So, into the second type of chemical bonding class, molecular bonding or covalent bonding. And from the terminology, we recognize what we're dealing with is the formation of molecular compounds. Or covalent compounds, forming covalent bonds or conforming molecular bonds. So the language and semantics of the subject kind of revolves around those two terms, covalent and molecular. Composition, of course, just to repeat, is of course equal to two or more nonmetals. So we're using the right side of the periodic chart exclusively. And along with hydrogen. Hydrogen's thrown into the mix. So you want to get that. Now, as these come together, they conform to the octet. We don't have any pseudo-noble issues here in terms of an individual element. It'll either be 8 or not, okay, except for hydrogen, which is 2 when it bonds out. So we'll have what we call the octet number. And when I say the octet number, it's 8. And you'll understand as we get into it. And it also means 2 for hydrogen, the duet, if you want to do that. All right. In molecular bonding, by definition, the valence shell will undergo a transmogrification or a change, okay, and which it has a paramagnetic electron, and it will look like that. It'll turn into a kind of a oblong figure 8 at one point. And then out here you'll have another element, hypothetically, that does the same thing, and it has a paramagnetic spinning the other way. And so what happens is these come together and overlap such that the electron pairing becomes diamagnetic. Okay? These are referred to, and we'll get to the names of them and what they're all about, are called bonding orbitals. However, when this takes place, that whole orbital structure, electron cloud, blends together like this. And it's just kind of like a sausage, squeezed into a sausage wrap. And this is called the covalent bond. And if that bond, here's a nucleus, say at the turn, right there. Right there. When that blends together, it changes from the name that we'll learn to be announced later, a bonding orbital, into what we call a sigma bond. And the characteristic of a sigma bond is that it is symmetrical about the nucleus. It has a line of symmetry through both nuclei. So if I draw a line through the bond, and we'll learn more about this, like I say, as we get deeper into it. That's got a line going through both nuclei here. Okay, and so that is the checkpoint for calling that a sigma, S-I-G-M-A, bond. When we represent that in literature, like this is, say this was carbon, right there, bonded with another carbon. We can do one or two things. We can use an electron pair to show that bond, or we can use a bar. And I put these out here because carbon has 4 bond sites. The bar designation or symbology is the same thing as an electron pair. One electron pair equals one molecular bond. Or covalent bonds like that. By far, the bar method of representing the bonds in a structure is used. You rarely see electron pairs used to indicate the bond. You will see it in structures that have what we call non-bonded pairs, which we'll say more about. For example, if you had carbon bonded to nitrogen, nitrogen will carry a non-bonded pair. But these other bars in here are bonded electron pairs. There's just terminology I'm trying to hit with you right now, guys. So don't get confused. I'm just hitting some high points so I can discuss the rest of it. Non-bonded electron pairs. Okay, so we'll be using the bar method to represent various bonds. Now, when these bars are presented, these are sigma bonds. So if I had a hydrogen all the way around here, all those are sigma bonds. They look like this up here at the top, but we put little bars around to simplify so we don't have to draw out the sausage-shaped bond in the thing, you know. But they're all sigma bonds. They used to be bonding orbitals, and you'll learn about that at the proper time. But when those bonding orbitals overlap and then start sharing their electrons, they change into sigma bonds. Now, there's only one other kind of covalent bond, and it's called a pi bond. Carbon valence level can exist in different forms. Okay, one of those forms, like if you have a carbon atom, can have a shape like this, and I will explain why in due time. Like this. So this is the nucleus, and there's your electron cloud. Same, looks like a big figure 8 going through the middle. Now over here you have another carbon, and a big figure 8 over here on the same one. Like that. Well, what can happen is that these two lobes, two on top, two on bottom, can overlap. And you'll have nucleus. Actually, you have the sigma in the middle. It'll be there. But you also have a big cloud above and below those nuclei. And it takes two clouds equals one pi bond. Now, when you look at this, like I say, it takes two of them to make a pi bond. What you're looking at is a double bond. When the orbitals, this is an orbital, bonding orbitals, they come together and they're called pi bonds. Pi bonds do not have a line through the center of the nuclei. bonding nuclei. They are above and below like that. And this is represented like this. I'm sure you've seen that in different books. Molecules got a bunch of double bonds or something in there. So it is a combination of a pi bond and a sigma bond. These out here say we're hooked to hydrogens. Those are single bonds. All single bonds. Write this down 100 times. All single bonds are sigma bonds. Now double bonds always have a sigma and at least one pi. Okay. The last one is where carbon undergoes a change or looks like this. Now you've got an orbital in and out of the board coming back and forth. And then you have another one over here that does the same thing. Back and forth, and this one. And so we have one in the front, one in the back overlapping, one in the top, and this one overlapping. Then you have this one coming together right here, maybe hydrogens hooking up out here. And this is a triple bond against two single bonds. You have two pi bonds and a triple bond, and one sigma, and the single bonds that are left open are sigmas. Okay, and they all result from overlap of what we call bonding, pre-bonding orbitals, and we'll get to what they're for. The highest order of bond is the third order. This is called a third order bond. Covalent bond. Second order would be double bond, and then you have single bond. And we have single bonds, double bonds, and triple bonds. Each bond is an electron pair. Same form of bond. For example, if we had a single bond, it would be one electron pair in there. A double bond would be two electron pairs in between the bonding nuclei. And the triple bond would be three. And I always have 4 bond sites on carbon, and so forth. Now these overlap, and so if I wanted to verify the octet, once they undergo bonding, the element must conform to an octet. Octet rule. Okay, so if we had methane, for example, you would find me writing something of this nature as a structural formula. Well, how do I know that's correct? Well, it conforms to the octet rule. All of these overlap. Inside that blue circle, I have 4 bars. Each bar is 2 electrons. 2 times 4 is 8. So that conforms to the octet. Hydrogen conforms to the octet rule by duet. And so when I draw circles around hydrogen in the bonding, see the overlaps in there? I have to have 2 inside of the circle for hydrogen. That's what I'm talking about. Now we're fixing to go into how to draw these things in a minute. Well, maybe then I got to talk about energy changes in formation of a bond and what happens here. But some of the terminology, one more item here. And we'll bring this back up when we get to A.V.O. Beck, how to draw Lewis structures and stuff. Let's consider the formation of molecular hydrogen, 2 hydrogen. So essentially, we're looking at a hydrogen plus a hydrogen ground state going to hydrogen, which is the same thing as H bar H. So that's what we're trying to prove and show how. Okay. Now, in molecular bonds, just as in covalent bonds, energy is given up when a bond is formed, and it is diagrammed as the two nuclei approach one another. They approach and give up energy as they approach one another until they reach what they call a bonding equilibrium distance, and it's called the bond length. And that diagram is a sideways T. So drawing a little diagram like this. The horizontal diagram is the distance between nuclei. Okay, and this is a potential energy axis. And typically you'll see people put a psi plus or a psi minus, meaning above. This is a zero line, so to speak, psi plus. Now psi plus here is particle-particle repulsion. Like taking two balloons trying to shove the centers together, the balloons will push back. And down here below the zero line is attraction forces. Okay. In forming a bond, hydrogen bonded to hydrogen out here, the elements start infinitely apart, distance apart. And so we have hydrogen and hydrogen whose distance from nuclei is infinity. Try to draw me a better infinity. No interaction of either one. So this being no attraction, this is zero attraction, no repulsion, no attraction. So we say that this case, step 1, is this point right there, 0 up or down. Now, as number 2, the hydrogens, say here and here, begin to attract one another. Even though they're distant apart, as one influences the other, the nucleus of one begins to attract the electron cloud of another, and the nucleus of the second one attracts the electron cloud of the first one. They begin to give up energy. And so a condition at hypothetical distance r between nuclei has given up some energy, and we find it is starting to give up energy. See how it's below the line. Okay, and we're still attracting here. And they get to a point where they are touching one another, so to speak, and they are attracting, so they are down here, and then they go into the overlap and bond right here in the diamagnetic pairing. Okay, and so that is the maximum loss of energy point. So you've lost energy right here. Here's the nucleus right here. The distance between the nuclei right here, see this point right here, is called the bond length. Now you have to visualize this kind of like two balloons coming together. You know, you got a center of the balloon, center of the balloon. Well, you can only push them together so much, you know, and without, kind of like a coiled spring. You pull the spring out, and as you get closer to, you'll reach a point at which you can lay the spring down on the floor or the table. Okay, that's neutral, so to speak, bond length. There's no attraction, there's enough attraction, okay, to hold the two nuclei close together, and they bond, but you don't have any repulsion forces, you don't have any tendency to squeeze together. So that's what we call bonding energy. So this point down here, So if we start drawing this, or filling in the curve right here, the depth of this right here is an energy term, and this is bond energy. The energy given up by a bond when it forms. Now, as we get on this side and we start pushing them together, we find out that the repulsion energy increases. You got two positive centers that you're trying to push together, like two centers of a balloon. The harder you push the centers together, the more the balloons push back up. And so there's a rapid increase in repulsion, so that inside that bond length, the nuclei begin to repel. And so they reach a point where they don't get any closer or further apart. Now, that's an example of just how energy changes take place. I'll come out here. Each type of covalent bond has its own bond energy. Okay? And we have seen this. We've used this in this table. So if we're talking about hydrogen-oxygen bonds or carbon-carbon bonds and chlorine-carbon bonds, each one, when it forms, goes through this energy transition process in which it gives up energy. And this is kind of a graphical illustration of the trends in the energy. We talk about bond energies. We're talking about the energy liberated when two nuclei reach their stable bond length. It's usually delta E B or delta H B, and it's defined as bonding energy, and is the energy liberated on formation of a single covalent bond that's specified by the energy. Specifically, hydrogen bonds to hydrogen, and I'm just delta HB, and I just make a little table here, is 432 kilojoules. Carbon-hydrogen bond is 411 kilojoules exothermic on formation. And as you would expect, endothermic on breaking. Okay, so if I want to break the hydrogen bond, I have to put in 432 kilojoules. Break the bond. Oh, well, if I'm going to make a bond, I had to pull the 432 out. So that's what I'm saying. Okay, and just a couple more. Nitrogen, hydrogen, and you have a copy of this, I hope. You'll need this next class because we'll be going into some of this. 386. Now, some of the bonding is multiple bonds, like you have carbon-carbon bonds, carbon-oxygen bonds, carbon-nitrogen bonds, where these are carrying non-bonded pairs and so forth. So just a couple of notes here. Carbon-carbon double bond is 602 kilojoules given up when that's formed. Carbon-carbon triple bonds 835. Let me see if I can find that carbon. There's a carbon-nitrogen down here. This is a 615. 745 kilojoules and then double bond. So when we talk about bond energies as they apply to a molecule, then a single bond is weaker than a double bond, which is weaker than a triple bond. So a triple bond would certainly, like, you can put a lot more glue in between the nuclei, and the bond's stronger. So we have increasing bond strength as you go left to right. And here, I don't see anything else that jumps out at me here. Now, energy trends, and you recognize this as we form a compound. I'm going to use methane. I realize I'm making a mess up here and running so fast. I want to get through this. Then we'll pick up with Lewis dot structures next time, after the quiz. The trend is exactly the same in concept as it was in the Born-Haber cycle, but this doesn't have any name, any formal name, but we still go through the process. To make a covalent compound, you have to have elements ready to bond. In other words, they have their valence electrons hanging out there ready to hook up with something. So we do start with the standard state equation. Carbon is graphite in the standard state. And we'll need a couple of moles of molecular hydrogen, and then this will undergo, it forms methane gas. The energy change here is the standard heat of formation. So we're starting with the basic elements of standard state going to a molecule. But if you put carbon, graphite, and hydrogen gas in a bottle and sugar it up, you don't get methane, because these forms are not conducive to bonding. You have to put them in bonding form. That means carbon has to have their valence electrons hanging out ready to grab the valence electrons of hydrogen. To get that process, you have to convert this to a gas, just like we did. That's atomization. Delta H atomization for carbon, and it'll go to carbon with its bond sites. So you atomize it and you pick it up, and so this is 0 and this is at a much higher energy. Same way here, you atomize the hydrogen, you have 4 hydrogen atoms which are ready to bond. And gas phase, and this is delta H, well actually it's 4 times delta H of atomization for hydrogen.
And where does the 4 come from?
We got to hook up 4 hydrogens with that central carbon. Okay? All right, so I got to have 4, like it or not. So the only place I can get them is from the basic standard state. Okay, now we're ready to bond. See, these are in a form with their valence electrons available for something to come in and pair. Pairing is the chemical bond, and so we form that, and delta HB for methane is the standard state, all the way through. And this, just like the Born-Haber cycle, we use the same trend. The delta HF up here for methane is equal to delta HA for carbon, standard, plus delta H atomization, 4 times delta HA for hydrogen, plus the delta HB. Then 1, 2, 3, 4. Yeah, you don't have these sublimation reactions here. You go straight from the basic standard state to the atomic form ready to bond, like that. So now we simply look up formation. Of course, this would be given on the problem. I got 3 minutes, I can put all this together for you. Methane is a minus 74.87. I'm going to round it up. It's minus 75 kilojoules. Right there. Atomization of carbon, 717 plus 717 kilojoules for, and it's one of them. All we have to do is one. Hydrogen, and it's 218, 4 times 218 kilojoules plus delta H of B. Now from there, I think you understand where we're going. That's all it is to it. Of course, I'll give you all the numbers. This is the only new part that you really have to look at. See, we're starting, all of these are 0, and that's at 0. And so the change that goes here is actually 717, because this goes to gas state at plus 717 kilojoules. Well, I learned to write a 7, I might be credible. Plus 717 kilojoules. So still, what is this? 717 kilojoules. 717 minus 0 is still 717. So that's what that is. Here, each one of these is 218. So you have 4 times 218 kilojoules minus 0, which is that. And then you have your delta HB. Each compound is going to have, molecular compound will have its own delta HF. And the only variation of this, see, we went straight to gas phase. Sometimes you have one that'll go gas and then condense, so that condensation will have to be another delta H number. Okay, now you can't do this with all the molecules, but this particular one you can do this. Carbon has 4 symmetrical carbon-hydrogen bonds. Well, if the total in here is 1664, divide it by 4, and you have the delta H for a carbon-hydrogen bond. So this works out to be 416 kilojoules, something like that. That's a 1 carbon-hydrogen bond. So using this diagram, we look at a carbon-hydrogen bond. And so this is how they're calculated. So they go through all the basic standard state numbers, and they come up with that. All of these can be figured using this diagram in the same way. Thank you, people. I appreciate your attention.